clients to provide a conducive environment for co-working spaces.
Okay, so next slide. Okay, so basically DFMA has many considerations that we could implement in our project, but I'm just going to elaborate on two. That is, okay, we will begin with point one, which is minimizing the number of components. So by doing this, you actually will help to simplify the construction supply chain and reduce the risk of missing components, delaying the progress of the project. So for example, we have opted for the use of column shoes in our intermodular connections because we wanted to avoid nuts and bolts that will like complicate the logistical process. So by using column shoes, you will still ensure that there is still vertical transmission of structural load through the building. Okay, then the second DFMA technique that I'm going to talk about is on point 4, passive design. So passive design are simple. They have few moving parts, no mechanical systems. So essentially they are fast free and that they require minimal maintenance also. So a major application is that in our building we have actually like an eastern corridor. So we actually inset all the rooms on the eastern corridor so that we can avoid morning and hot afternoon sun. So this will actually help to reduce our air conditioning costs and result in energy savings at the building level. Okay, next. Okay, so basically we have two models that greatly help us in evaluating the different thought process for designing components. So first is that of functional analysis. So basically you actually evaluate whether each and every single component is crucial and essential to the whole building assembly. So if it's not, then you either combine the purposes of the component so that you can actually have lesser components doing the same job. Then the second thing is that of a flowchart. So this flowchart actually considers you have customer requirements, you have functional what's the word? Okay, I forgot the word, but basically you have a functional requirement of the product. So it basically shows that design is a recursive process. You just keep on going through improvement, whereas here. So a construction project is inherently complicated because it involves many stakeholders and it's very large scale. So we use Microsoft Project to basically identify the task breakdown, the costing, the resource allocation, all this through Microsoft Project. Yeah, so Microsoft Project was able to help to act as a platform to consolidate all of this information. So using the same program, Microsoft Project, you could actually find the critical path of the program. So critical path is basically identifying which are the most crucial parts of the project that cannot lag in the overall construction program. So this will actually help in reducing the time taken and then reduce the risk of project overruns. Okay, so now I'll pass the time now to Li Hing, who will talk more about the analysis that we have carried out in our project.
When we started designing our building, right, we came up with what all the other teams did, which is we came to a drawing board and we started to come up with some ideas. But actually, through some research, right, we actually found out there's actually a even more crazy way to do it. So I'm sure all of you have heard of AI and computer science that's emerging in engineering nowadays, where the computer can generate thousands and thousands of models, right? And you can actually test those models to see whether which one fits your optimal parameters which you set. So we decided to use Autodesk Refinery, which is actually it uses Dynamo script to run. So what it can do, right, is you can set parameters on a variable scale. I want the room to be how big, no matter, I don't even care how big it is. You just set on a variable scale, right? And it will generate a room that has the optimal window to room depth ratio or amphitheater seats in the right configuration with the maximum amount of seating capacity with the least amount of height, for example. So we actually use this, and so on your right you can see the AI has generated two models which fit the parameters which we set for the room width to height ratio and stuff like that. So it's some of the stuff that we did. So using this, we could actually like design some parts of our building, right? Using like not using kind of like our mind, it's actually using the computer to generate these models which are highly optimal and efficient. But of course, all these models have to be evaluated manually nowadays, which is, so what we did was during our first iterations, we found out that the lighting was too much into the rooms. So we decided to use the sun shading in order to to shift away the sunlight from the room, and it will help us with our cooling as well. So this is just some of the color shades that you can see, how the sun shades actually affect the shadow of the room. And on the left side is the total amount of power that's needed to cool the room at 24 degrees, based on the rooms that have air conditioning, because mostly the office rooms have air conditioning. And on the right is a solar analysis of how much power that we can generate if the whole roof is lined with solar panels. This building is not net zero, it cannot fully sustain itself with solar. But on the left side, right, the amount of power that is needed, which is roughly 6 times the amount that the building can generate. Actually, this is based on a 24-hour, 24/7, 365 days air conditioning of 24 degrees. But we believe that if we implement occupancy-based cooling, as well as like some green features as like based on how many people are inside, or only like certain areas with like basically smart cooling. So we use smart devices to detect the number of people and actually like analyze the cycle. Then we believe that we can reduce the amount of energy cost in the building, and as well as using LEDs and lights and stuff. So just to emphasize more on this like computational design, right, which can be called generative design, using AI to generate rooms. So for our amphitheater, right, we actually came out, as you can see on the left side, like we gave the AI, like it's not really AI, but yeah, it's kind of like AI, it's a smart AI. So when we told the AI that we wanted the most number of like seats, right, for a certain width, then what the AI did was it gave us those like models, and we can tinker with it so that we can find out the best way, right, to fit like a room of that size that we have allocated with the maximum amount of seats, with the best viewing angles and everything. So we don't have to go through that whole process of coming up with multiple like stages and re-evaluating and re-evaluating. We can really start from scratch to design a building that is fully optimal based on science and mathematics. Of course, we will have done this more for other parts of the building, but this is pretty complicated. So like this is what we have done so far. And now I would like to pass my time to Yash to talk more about the AR and VR technologies that we use.
Okay, thank you, Li Hing. So besides using software to optimize the design of the building, we also took advantage of AR and VR to analyze the building. One such software that we use is this software called Modelo. Basically, it's a free software for us. So what we need to do is that we need to upload our building through their collaborative online platform using the Revit plugin. From there, it will generate a URL code for us, and using that link, any of our team members can actually access the building. The benefit is that we don't really need additional software besides the plugin, and all we need is to enter the URL in our web browser, and we are good to go. And the interesting part is that if we were to enter the URL web browser on our smartphone, we actually have an option to turn to enter into VR mode and turn our smartphone into a VR device for us to explore the interiors of the building. So this is some of the screenshot of our model. One benefit is that it allows us to view the building and detect any design flaws or any design errors in our building. An example of such an error which occurred is, as you can see from the screenshot on the right, this is actually this section here is actually our exhibition hall. What happened is that when we run our analysis for the aircon, we actually had an error because our exhibition is actually stretched to 2 floors, but we didn't extend the side wall to the second floor ceiling. So because of that, we had this wasn't enclosed, and we had an error when we tried to run the simulation for the energy consumption of our aircon or air handling units. So this example of using some design clashes in this 2017 study, which is using 2Ds instead of 3Ds, and also design errors. And we actually looked through this study, and we tried to implement ways whereby we can reduce design clashes in our project. So what we did is that we took a collaborative approach in this project where we do interdisciplinary checks, and also we define certain key elements such as the origin, orientation, boundary, grids, and levels. Okay, so moving on, I would like to pass the time now to Kain to talk more about our collaborative platform and lessons learned.
Thank you, Yash. And now I'll be presenting on the BIM 360 design, which is a platform for all of us to come together, even with different specializations. Okay, so BIM 360, one of the features that we use is the Revit Cloud Work Sharing, which is an integrated workflows with a permission system. So you can add the members in our teams and just give different permission allowance. Another feature is visual timeline where we can actually share data and packages to our teammates, and we are able to identify what are the changes with the color codings. So our next slide, please. So our team has benefit greatly from the softwares, as it helps us to centralize the data and manage the data throughout the whole project life cycle. One of the examples is shown on the slide, where we experimented around to achieve the best roof and shape designs. Another example is we use this to identify clashes, where and in one of the cases we identified some HVAC pipelines that are running through some columns. Okay, so to conclude for our projects, we have used various softwares, including BIM 360 Design, Dynamo Refinery, Modelot, as well as the Microsoft projects to achieve these to overcome these four key challenges. And on top of that, we also gain more understandings on the concepts of green building designs, IDDD, DFMA, and how they are applied in construction project today. With that, we sincerely thank the organizers for the learning opportunity. Thank you. Now comes the Q&A session.
Yes, sure.
So primarily for our building, because we identified that PPVC use couldn't be very extensively used throughout our building, because there's very little potential for repeating units. So in terms of construction, we are primarily using precast. But in terms of PPVC, we do have repeatable units. I mean, we have our lift shaft, our stairs, our toilets. Yeah, so all these units are PPVC. I think we have like floor plans available in the report. No, in the poster. Yeah. So we okay. Just hang on.
Keep the mic to the rest of your
Yeah.
So while research, because that was also similar. So other than your same thing, your concrete component, that structural concrete component, which is precast. So the PVC is not clear. So we want to see where is your PVC. So these are the main items.
Okay, so while we don't have a PPVC plan per se, but what we do have is a typical floor plan. Okay, so what we have here is the toilets. So these toilets are going to be repeated throughout the 4 floors. And then we have split them into male toilet, female toilet, in between handicap toilet. So we will split this toilet module into 2 because for transportation, for ease of transportation. Then basically we have our lift shaft and stairs, and that's the first set here. Then we have the same thing over here. So basically we can double the use of PPVC. Yeah. Then yeah, that's our PPVC for this project.
Anything else? Can you talk a little
bit more about your computational approach. Is this used to, do the height to width ratio?
Yeah, the window height to room depth ratio. So like this, we set it to 2.5, right? So we can actually make millions and thousands of rooms of different shapes and sizes. And especially for the amphitheater, right, that part where it can generate like the right amount of seats for your room. So you don't have to like just plug and play into the room. You actually have an optimal system that is fully high seat capacity and yet like comfortable enough. So we really maximize the space, and it is inside the program script lah. So it cannot go wrong. So yeah, that's why we used to make the amphitheater, like the seats and stuff, so we can fully utilize the space.
So what are the key parameters you use to do that?
So like some of the parameters, like just give me a moment. So yeah, like there's the total width, curvature, the aisle interval, like row count, steepness, incline. So yeah, so this is what we set. These are the parameters that Dynamo can measure, right? You can actually set them in Dynamo. Like I measure the length of the room, the width of the room. So but the thing is like the current Dynamo which everyone use, right, is you guys must have a certain value. So but this one is actually variable. It's like blue color, so it actually can change and you can see in real time. So like as of right now, I believe it's possible to do like actually like you have a building model, you can actually turn the building model to have the optimal shading and stuff. Like it's capable of doing that right now, but we just weren't able to implement it inside because it's very lengthy and all that. But so it is actually possible. Like if you have a very big precast concrete slab, it can, or like a wave shape like our sunshades, right? You can actually split the shape into similar shapes where you can use it in a PPV, like in a sub. Like you can, rather than having a giant sheet of wood, right, you can actually split it into a shape that is homogeneous that you can use repeatedly, so you can generate complex shapes. So in a way, you can have that capability, but we weren't able to reach that stage. So yeah.